on this series of yes, I need to do something. No, I think it's okay. On this series celebrating 10 years of Deezer research and R&D in general, Hugo was an intern in 2017, which is quite a long time ago. And since then, he has become a doctor and is now doing a postdoc at ISIR, which is the same lab that is now welcoming Agnès that we saw last week. Thank you, Hugo, and the floor is yours.
Thank you very much. So yeah, I would like first to thank Manuel and all of you for welcoming me here today. It's a great pleasure to have this talk and to meet again all of my previous co-workers. And so today I'm going to talk to you about something a bit different of what you might do here in research, but might be related to. So it's still interesting to know this type of things. And so I will talk about pedagogical demonstration and pragmatic learning in artificial tutor-learner interactions. So it's a work that talks about reinforcement learning and social interaction of different artificial agents, what social interaction they can have. And so I'm doing this postdoc under the supervision of Olivier Sigaud and Mohamed Chetouani, which you might know or not, but yeah. So the big picture of the research that I'm conducting in this postdoc is about creating artificial agents that possess different type of properties, mainly the fact that it can be teachable and the fact that it can be autotelic or autonomous. I will explain what autotelic is. So basically it comes from this line of research comes from the fact that autonomous discovery and direct instructions are two types of way you can learn infants so that they become intelligent. And in education science or the developmental psychology and cognitive science, they show that mixed approaches such as assisted discovery or guided play almost always result in improved skill acquisition. And so in the field of machine learning, which and reinforcement learning, which I've been working on during my thesis, these two types of properties are often treated separately. And so you would have autonomous agents that learn from their own signals, and then you would have interactive agents that learn with teachers, with, let's say, instructions or demonstration and different types of teaching signals. And so in our line of research, we try to create a type of mixed agent that can be both teachable and autonomous, which we call teachable autotelic agents. And so they can learn with both internal and teaching signals to get higher efficiency. So the term autotelic is something that is important in my lab because in the field of reinforcement learning, they are actively trying to create agents that not only learn from rewards that are given with the environment, but creating agents that create their own goals and try to pursue their own goals. And so the idea of autotelic, it's a Greek term to say I'm creating my own goals. And so the idea is that also infants, they tend to be curious and try to learn without having something clear in mind to do, but trying to just pursue what they want basically, and creating own goals or trying random stuff. And so this autotelic term is associated to many approaches in the lab with reinforcement learning agents that learn this way. And so my work is more on the teachable side. So I'm more interested in the social interaction that these agents can have with teachers. And then my work is also based on autotelic agents. So I will not create new approaches for autotelic agents, but more trying to take the autotelic agents and then make them teachable. And so improving how they can interact with social partners. So for this work that I'm presenting today, I'm mostly interested in, I'm taking inspiration from developmental psychology and most specifically from an approach created by Guéon, which is called inferential social learning theory. So she's a developmental psychologist that tries to that has been studying infants for many years, and now she's getting more and more. She is trying to put her research to work in the machine learning community, and so she's trying to have an impact on how machine learning scientists create agents. And so that's how we came across our work, and we were very excited about this work. And so we wanted to follow her advice, take some advice from her studies on infants, and try to apply that to artificial agents. And so what she says is that in the mind of machine learning scientists, we tend to have the wrong assumption about how people learn from others. And we might say that social learning means copying or imitating, following advice. We might say that social learning is different from individual learning, or that social learning is not teaching. And so as a result of these wrong assumptions, the machine learning scientists might create agents that try to learn from others without understanding why, and then as a result cannot decide when to learn, what to learn, and whom to learn from. So in her research, she tried to paint different pictures and present her studies on infant as a justification for those approaches. Her main theory is about inferential social learning and how you can learn from evidence that is generated by other agents. When we say this, we say that agents might create teaching signals in many different ways, even though it's only as data, demonstration, or language. So for instance, you might have incidental actions that are actions performed without a clear goal. Then you might have instrumental actions. So let's say you're in your kitchen, you're preparing yourself a meal on your own. You're going to do all the optimal actions to cook your meal and not care about showing something to anybody. And then you have instructional or pedagogical actions that are actions with a communicative goal. So if you're in the kitchen and you're trying to learn to make someone learn about a particular recipe, you might exaggerate a few things or show how to make the recipe a little bit differently than if you were on your own. And so by considering how the information is generated, then the learner can draw different inferences from the same data. So this type of thing is especially powerful when the evidence comes from teachers, and that's what we are interested in. So finally, the main conclusion from our work is that we should create generative models of how other agents think, plan, and act. So as you can see here, the teacher might select data by considering how the data would affect the learner, its goal, its belief. And then the learner can interpret the data by considering how it was generated. Is the person teaching me something in a pedagogical mode or not? And this type of questions might be interesting for the agent to ask itself in order to better learn. In our case, and in the research that I'm going to present today, we are trying to apply this inferential social learning concept to learning from demonstrations. So we will not talk about language, for instance. We're only interested in actions. And so the two main points is that human demonstration involves pedagogy with showing rather than doing the task. And also a very crucial concept is to disambiguate between different goals and trying to make the information clear. And also human learning involves pragmatism with learners that try to interpret what the tutor communicates, and they just relevant information. So in our work, we say that our contribution are to adapt pedagogical tutors and pragmatic learners to AI learning setups, which is not currently done at the moment in the field, and to provide analysis of the benefits of adopting such approaches in terms of AI learning setups. So for now, we'll present all of my work on a toy environment so that you can understand how it works, how we create pedagogical teachers and pragmatic learners. And then I will present a more elaborated example on an environment that's a bit more complex. So this environment that we created is called the Draw Two Balls environment. It's very simple and adapted from the work of Guillaume, and it purposely introduces goal ambiguity. So the goal of the task in this environment is to pick two balls consecutively, and then as a consequence, you can have different types of goals that are reached depending on which balls you choose. So basically, if you take orange and pink orange or orange pink, you will get goal 1, which can be characterized by some kind of sound. That's something related to the original environment of Guillaume. And then if you pick orange pink, you will also get the goal 2, which is where there is some ambiguity. And otherwise, if you pick any other actions, you won't have any goals that are reached. So the first phase that we do in our work is to create the teachers. So we create the naive teacher. The naive teacher is not a teacher that cannot solve the environment. It's just a teacher that only tries to master all of the possible goals and does not care about being pedagogical or not. So you can call it also an optimal teacher, but optimal is not really the right word here. So we call it a naive teacher. So it's trained to master all goals using policy improvement, and it rewards itself and updates its policy when trained to reach goals. Then we will create the pedagogical tutor that is the same as the naive tutor. It shares the same architecture basically, but the pedagogical teacher uses a Bayesian mechanism to predict the pursued goals for its own trajectories. We'll come back to that later, but that's the key insight from this research. And so it does so by updating its policy to better predict goals for its own trajectories. So the implementation details of the naive teacher, how it's created. So what is the policy of the teacher? It has 3 policies, one for each goal. So the goal 0 is achieving no goal, basically. So it might be called goal 0. So it has 3 policies, one for each goal, that are composed of probability distributions. One policy for one goal would be the probability of picking the first ball, which is presented here on the left. And then you have the probability of picking the second ball given the first ball. And so you have 3 possible probability distribution depending on what is chosen for the first ball. How it learns, how the teacher is created, is that it explores the environment and randomly discovers goals through exploration. And then it samples among the discovered goals, play its policy by sampling the probability distribution, and it adjusts its policy according to the reaching of goals or not. So here is the full naive teacher policy with the probability distribution for each goal. Then, a little bit more interesting, you have the pedagogical teacher. So the idea is that human teacher often emphasize or exaggerate certain aspects of the task to better demonstrate it, as we said. And for the teacher, one thing that is important here is goal disambiguation. And in our case, it will result from using a goal prediction reward. So when the pedagogical teacher learns to solve the task, it modifies its policy to be able to achieve the goals, and also to when it produces a trajectory that reaches the goal, it should be able to, if the trajectory is given to him, to predict what goal was pursued in the first place. So intuitively, it will be easier with this demonstration for the learner to predict the right goal using this. So basically, we are kind of the teacher asks itself, what if an external observer would observe my demonstration? Would it be capable of predicting what goal I was pursuing? And so that's why it's kind of a mind theory of the other agent. So we implement this pedagogy system with Bayesian formalism that is introduced in another paper by Mark O, who is a developmental psychologist and also a machine learning scientist that works in the same line of research, but mostly it tries to also do human studies with this type of formalism. And in our case, we try to apply it to artificial agents. So it implements this goal prediction using the Bayes rule, and basically it tries to compute the probability of the goal given a distribution, which is with the Bayes rule proportional to the probability of a demonstration given the goal. And what's cool about this formulation is that the probability of a demonstration given a goal, you can actually compute it with the policy and the fact that the environment is Markovian, so that one state only depends on the previous state. So this you can compute this probability, which gives you a way to predict, to give a prediction about a goal given a demonstration. So what you do is that when the pedagogical teacher makes a prediction about a goal given a demonstration, it will reward itself more if it's able to predict the goal clearly. So here you can see the full policy of the pedagogical teacher, and if we compare the two, what we can see here is that with pedagogical demonstration, there is no ambiguity regarding the pursued goal. So, for instance, let's say you want to show goal 1. If you're a naive tutor and you don't really care about showing to other people, then you might do orange-orange or pink-orange or orange-pink. But as you might have seen, if you do the demonstration orange-pink, you also show the second goal. And so for an external observer, you cannot really tell if the other agent is trying to show goal 1 or goal 2. And so that's why the pedagogical teacher only select the pink-orange demonstration. You can see here in the policy, and so it considers that it's the only way to show unambiguously the goal 1. And you can also even emphasize on that the pedagogical teacher even tries to only select the pink ball as the first action, because if you select the pink ball first, there is no ambiguity because there are no way to show goal 2 and starting with a pink ball. So basically, it's the optimal way to show goal 1. So that's why the pedagogical teacher use this. So remember, this is only the teacher, and now we have to create the whole teacher-learner setup, which we were interested in the first place. And so, as I said in the beginning, we are creating agents that both learn from teaching signals and on its own. So the learner receives demonstration, attempts at predicting the associated goal, and rewards itself for correct prediction. But then it attempts at reaching the predicted goal and explores the environment this way and iteratively updates its policy to master all the goals. So this is the naive learner or literal learner, which is basically the counterpart of the naive teacher. And then you have the pragmatic learner, which is the counterpart of the pedagogical teacher. And it's the same as the naive learner, but it also adopts the same Bayesian mechanism for goal prediction, because it biases the policy towards a policy that is able to predict goals more easily. And so it kind of prepares itself to be in a pedagogical mode or learning mode. And so that way it's better able to understand the teaching signal. So we implement this in the same fashion as the pedagogical teacher. And so the implementation detail for the naive learner is that it's the same policies as the teachers. The teacher provides a goal, a demonstration with a goal. The learner predicts the goal, G hat, and then it places its policy condition with G hat and achieves GA. And then it gets a reward if if the prediction is correct and if the achieved goal is the pursued goal. And then the pragmatic learner, it's the same thing, but if the trajectory with which it achieves the goal is something that it's able to predict the goal from, and then it also gets an additional reward. So now we can talk about some of the results. Here you have the four different configuration that you can have in the teacher-learner setup. So literal learner, naive teacher, pragmatic learner, naive teacher, etc. And what you can see is that agents that are trained with pedagogical demonstration are able to have a 100% predictability on the demonstration of the goals of the demonstration, whereas the learners that are trained with the naive teachers are only able to do 80%, and basically for the learners that are trained with naive teachers, the error on the goal prediction comes exactly from the ambiguity problem that I showed you. So that's the first result, and then the second result is are the learner able to also master all the goals, and how fast can they do this? And what we see here is that learners that are trained with pedagogical demonstration learn faster, and pragmatic learners learn faster too. So basically, the two mechanisms help in predictability and reachability speed. So that's the first experiment that we conducted on a toy environment, and there's no reinforcement learning involved. It's only like a policy iteration stuff. And so now we're moving on to a fetch block stacking environment that we are used to work in our lab. So bear with me here because these are work in progress results. So I'm currently working on paper and something, but so I didn't really have the time to. So that there might be some illustration that are a bit rushed and things like this, but basically we have some of the results that I will present here. So this environment is made with the Fetch robot, which is a robot that has a 7 degrees of freedom robotic manipulation arm. It's adapted from Akaxia, who is one of my coworkers in the lab. And the environment, the goal of the environment is to stack different blocks, and so to make stacks and put some blocks close from each other. And it also presents goal ambiguity. And it's also a natural testbed for experiments because block stacking is something that is widely studied in developmental psychology. So it's really natural for us to have the same testbed with artificial agents. What is the goal space of this environment? How do we define it? The idea is that we define predicates, which are relations between cubes that are given to the agent. So the goal space is basically a different configuration of block stacks. So you have in blue here the close predicate, which says that if different blocks are close from each other or not, and then you have the above predicates that tells if one block is on top of another or not. So you have examples here. If the red and green are close to each other, then close red green and close green red are 1. And with the symmetry, you can boil down to only three close predicate and 6 above predicates. Here I will play a little video with the training. So it comes from the paper of my coworker, and so he created an autotelic agent that is able to train itself to discover goals. So discovers goals randomly through exploration, and then targets those goals to get a little bit better and better. And so after a few epochs of training, it's able to, for instance, succeed on only the close predicates or only a few above. And then in the end, it's able to master all goals in the environment without any supervision and without reward function as well. So that's it for this. And so here I will go over this slide a little bit quickly, but it's the architecture of the autotelic agent. So the slide's pretty ugly, so sorry about this, but basically what we use is that there is a goal generator. So that's the autotelic part of the agent. It produces and generates its own goals. And then the architecture of the agent, it's a reinforcement learning agent. It's trained using soft actor critique, which is a reinforcement learning algorithm, and its architecture are graph neural networks, which you know here, because it implements all the relation between the cubes, and it's really convenient here. And then basically the AI agent produces trajectories with goals, and then those trajectories are relabeled through inside experience replay, which is a technique that serves to relabel different trajectories with the achieved goal rather than the pursued goal to get more reward, so that it's easier for the reinforcement learning agent to train. And then it's given as a feedback loop, it trains itself, and it works. So this is some work that I'm using in my work, but the goal of my work here is to modify this learning setup to add demonstration and teaching signal, and to see if it helps to implement pedagogy and pragmatism. So what are the type of goal ambiguity that we have in this environment? So depending on the starting situation that is given to the agent, there might be two demonstrations that are identical, but the intended goal is different. So let me show you this video. So for instance here, I can't really see well on the left, but here at the starting position, you have green and red that are already close from each other, and the goal is to put the blue next to red, and to put red next to green. So red is already next to green, so the naive agent will put blue next to red. Sorry. So that's exactly what the agent does. Puts blue next to red. But then if we see this same example with another goal, let me see, I have to so here we have the same starting situation, but the goal is only to put the blue next to the red. And so for the naive agent, it says, okay, if I'm just being tasked to put the blue next to the red, even though the red is already next to the green, I'm just going to put the blue next to the red, and that's it. I succeeded in the goal. But yeah, as you might have understood, this as a demonstration would be ambiguous regarding the pursuit goal. So these are the types of ambiguities that exist in this environment. And so we will do kind of the same thing, create the naive tutor and the pedagogical tutor. The difference here is that the tutor is still trying to master all goals, but using all the mechanisms that I showed you previously. And the pedagogical tutor is the same as the naive tutor, but uses the Bayesian mechanism to predict the goals for its own trajectories. And what we can do what we can see in the end is that the pedagogical teacher does extra steps to disambiguate between confusing goals. So for the same example, what we have here is that it will move different cubes to have a demonstration that is different and non-ambiguous. As you can see in the last example, he removed the red and moved it to the blue rather than moving the blue and put it in close to the red. Okay. The training loop here is a bit different because so you have the same type of idea where the policies of the learners are the same as the teachers. The teacher provides a demonstration with a goal. The learner predicts the goal associated to a demonstration. And the difference here is that here, if the goal prediction is correct, the learner is able to take this demonstration and to put it in its own replay buffer that will be used in the reinforcement learning algorithm. So it's the same type of idea, but since we're working with replay buffers here, this is how it works. And otherwise, it's kind of the same thing, apart from the end, where in the end, the agent has to learn with reinforcement learning with experience that is collected on the environment on its own and demonstration. So basically, you have a learning from demonstration algorithm that you have to apply here. And we use a soft QA imitation learning, which is a very simple method in which you will relabel the demonstration and the experience trajectory with different types of rewards, and you will put a high reward on demonstration and a low reward on experience, in order to force the agent to imitate the type of thing the teacher does. So if you're interested, we can talk about this later, but it's a usual learning from demonstration technique that we use here. So the type of result that we have here is that, so we tested the approach with 100 demos per goal, and then 500, and then 1,000 to see what is the impact of learning under different types of demonstration regimes. So what you can see here is that when we have very few amount of demonstration per goal, we can see that the learners that are trained with pragmatic mechanism or pedagogical teachers are able to have better results on predictability and on reachability as well. Here it clearly shows that the best approach is to have pedagogy and pragmatism. And then once we get more and more demonstration, the difference is slimmer and slimmer. And then you can see that, but in the end, you can still tell that the pedagogy is still useful, because the predictability will always be higher with the pedagogical teacher compared to the naive teacher. So the conclusion and takeaway messages from this research is that learning in a social context with artificial agents is not different from learning in a social context with humans. We can draw inspiration from all of the cognitive science and developmental psychology research. And that, as we saw, learning from demonstration can be enhanced with pedagogy and pragmatism, which improves predictability and training efficiency. For the future work, so the short-term future work is to write paper and things like this, and to also compare pedagogical teacher and naive teacher, but in a more systematic way. Here I just showed like an illustrative example, but maybe we can have something a little bit more systematic, where we saw all of the type of vulnerabilities that might exist in the environment and characterize them and show how the pedagogical teacher solves them, and to also perform some evaluation studies on several algorithmic design choices that I made. And for the rest of my postdoc, I will try to study those scientific questions, where I will ask myself, can the learner have more complex pragmatism mechanism? So there is a lot of research on inductive generalization. So basically deducing stuff from what the learner is trying to teach with inductive generalization. And also to study what happens when the teacher makes a mistake, and how can the learner evaluate the teachers too, which may be useful in different setups. So I would like to add something about Deezer research. So basically, I started my research journey here, and as you see, my top cited paper is still the paper that I made here. So I'm really glad to have this kind of memory of Deezer research in my Google Scholar, and so I hope it still continue. And I think it goes to show that Deezer research is useful, and that good research is made here. So I'm proud about this work, and about you guys as well. And if you're interested in the paper, it's an archive, like a very short version that is published in the workshop. But yeah, it's still available. And if you want to contact me or you need the figures, here are some of the contacts. And thank you for your attention.
Much. We have time for some questions. So, we have Elena online. Go ahead.
Hello, hi Hugo. We've
Hello.
met actually, because I joined Deezer afterwards, but really nice work. Yep. And very nicely presented. I have a question actually about your last, if you can go one slide back.
Yep.
This not about was about the teacher work. It's actually related to your second question. What if the teacher makes mistakes, and how can the learner evaluate teachers? And this made me think of Many years ago, I used to work on multi-agent systems and multi-agent systems, and I think they were pretty famous, this reputation and trust models. And I was wondering if this is still used nowadays in the domains, and if you have considered implementing such a thing, for instance, for identifying the errors or, putting an extra layer.
So I'm not really familiar with this type of literature yet, to be honest. But the main question that I want to ask on this is more to because this type of research is also related to human-robot interaction. That's why we're interested in the fact that in the question of what happens if the teacher makes mistakes. Basically, because human might do some pedagogy and try to be more communicative about their goals and their intent and the way they make someone learn, but they also make mistakes and they are not as optimal as artificial agents. And that's why this type of questions are important in this research. So I don't know if it's related to what was done in the multi-agent stuff, but it's more human-robot interactions, I think.
Right. I think it may be related because those models were also on building trust given the interaction that was in the past. So either it is a human agent or but okay.
That's definitely
I've seen it a long time ago, so that's why I was wondering if you are aware of it and if it's something. But
no, that's not something I'm really aware of. But I should look into it. Then. Thanks.
Thanks.
Yes, Darius.
I had a question / concern on how much of this research is anthropomorphism in the sense that we may just apply human pattern to AI agents that don't reason like humans.
Yeah. So that's
have this limit.
Definitely a good question because there's no I understand the point in which you say that artificial agents do not need to copy humans to achieve some type of intelligence. But for me, I was concerned about this as well in the beginning of my postdoc. But I think what's interesting is that the literature on developmental psychology is broad enough to have so much ideas that you want to implement, and it may be harder to come up with something that is really useful for an artificial agent because we do not know how to study them. So I think what's cool about trying to apply those human concepts to artificial agent is that you basically have more inspiration and more facts to use to try to implement and see if it works or not. Otherwise, if you're working on other type of idea, the only way you have to the only kind of way you can work is just to try things out and see if it works. And so I guess it's a little bit less systematic, especially with reinforcement learning and deep learning in general, which we don't know fully yet how it works theoretically. If we would have this theoretical understanding, I think it would be interesting to kind of use it in our advantage to optimize the way agents learn. But since we do not have this yet, I think it's more systematic to do so with cognitive science research.
Okay. I was actually wondering if the reason was to have something more interpretable in the sense that we see how it is structured, its reasoning, and so we can follow it.
So I think also one of the motivation behind this anthropomorphization is that lots of this work are, as I said, used in human-robot interaction. And in human-robot interaction, you need to be to interact with humans. So this type of behaviors are especially wanted. So in this sense, is useful. But for me, I'm not really interested in having agents that interact with humans, but just to find ways to improve how you can make artificial agents learn, and it's a way to try. So why not? But I understand the concern, of course.
We have a second question by Darius.
Yes. One about if you have like confounded goals, because you mentioned this entanglement of goals, but what if you have, like, for instance, goals that need composition of several intermediate goals? Do you manage this kind of case?
That's actually
Thought
a
about that.
really good question. That's something I'm a little bit interested in. I think you might have more and more confusion as you add different type of dimensions in your goal space. Like so, if you have sub goal space, basically you might have confusion between sub goals or like in the sequence of goals that you have to use. And that's something we're actually interested in, because in the autotelic agents construction, you have some hierarchical stuff and things like this. So that's definitely something that my coworkers are interested in. For now, I'm mostly interested in goal spaces where you just only have
Independent.
they're kind of independent, and but actually we are considering this, and we might work on this on future work, because it's a natural way to expand how autotelic agents learn.
We have a follow-up question on that, and on this entanglement and intricate goal thing. What about causation and causal inference related to what you do? Is there some possibility of introducing some causal inference to learn some like causal patterns that you may have in the teaching?
Mm-hmm.
Is this something that you're interested in?
So I was interested in causal inference during my thesis, but I didn't put much thought about applying this here. Like, how would you apply it? Like,
That's my question.
Which type of intuition you would have?
Maybe
that it would help you.
Yeah, I'm not sure for like very basic stuff, because causation may not be well defined. But if you have, I don't know, if you're learning to, I don't know, build a tower with little blocks, then you have to have some kind of understanding of gravity and the cause of gravity on what you're doing.
Okay. So that's actually
that's a possibility, but there are also a lot of other possibility, but that's one of the.
That's actually very interesting, because so here the example is presented on 3 blocks, but my coworker has been working a lot on the 5-block setup, which is much more complicated, because you have like a 35 configuration with 3 blocks and like 70,000 with 5 blocks. And so what he saw, he had a lot of trouble scaling up his approach to 5 blocks, because the agent is used to taking so to make blocks of let me remember what is the problem. Like the agent is to create a stack of 3 blocks. It will take I think it will take 1 block and then put it on the other, and then put the 2 blocks and put it on just 1 block. And then when it gets a little bit harder, it's really hard for the agent to take 1 block of like let's say 4 and put it on the 5. So there are lots of problems like this where it doesn't scale up, and you need some kind of understanding of the environment and causal inference to do so. So I think he solved the problem like in a deep learning way, like just making your model a little bit smarter and avoiding the problem. But I think there's definitely something in because the way you do things tells a lot about how you understand the world around you, and that's basically also something very crucial to this research. So I think it's a very important question that should be researched as well. Yeah.
We had a question over here.
I was a little bit more naive. Can you go back to the first example when you were showing the result, the difference between with the results?
Okay.
This one.
Yes.
Here. So I was wondering how good is going to be the new teacher, the pedagogical teacher, in order to overcome the limitation of a student that has already learned some some ambiguities in the policies. Is the teacher able to this policy, this ambiguity that the student already know. For instance, the one that you train, the blue one, if you kind of now you change the teacher and you put the pedagogical one, is the teacher going to be able to help these students?
Okay, so let's say a learner is already learned a policy that is not suited. Yeah, okay, that's an interesting question. We didn't investigate yet the kind of temporal stuff. We are just making training in one block and not trying to see, because a big question also of this research is when to teach. When teaching is enough, or when teaching should be finished, basically. And so considering this temporality is something that is interesting, because in human-robot interaction, and it's a very fundamental question, because if you think of an open-ended learning environment, you might learn something, then unlearn something, and forget about things. And so for the moment, I guess that with this type of algorithm, I think if a learner is trained in the wrong way, it's kind of definitive, you know.
Okay.
But I guess you would have to add something to kind of still have some kind of room for exploration, even in the teaching senior, saying that, oh, the teaching senior has kind of changed. Maybe I should reconsider my policy and change it. Yeah. So I would not think I don't think it would work here, but it's definitely something we're interested in as well, and trying to have different phases of learning, and so that the teacher-learner setup is more and more interactive.
Yeah, no, totally, because this adaptability is something that could be put in mechanism already in the way that you are training, that is thinking in the future that this is something that can be rethink and readapted.
Yeah,
could be really interesting.
Yeah, I used to work on the continual learning as well. Yeah. Which is really rated, and I think adding continual learning to this type of approaches is something that's pretty relevant.
There must be some sort of phase transition in the learning process, like a tipping point from which we cannot really recover.
And it's and then all the stuff from Guillaume makes sense also, because you should have a generative model of how other things plan and act, and so you should be able to detect those tipping points and try to recover from them. And so basically, if you have a generative model of how the other agent think, maybe you can take those consideration and do something about it.
Right. Do we have other questions from, I don't know?
I have one.
Yeah, sure.
Why do you consider that a good pedagogical teacher would be one whose policy is more easily the goals more easily predictable for the...
So that's really something that's taken out of developmental psychology studies. Basically, what they say is that goal prediction is a very important way that infants and parents communicate with. Basically, children usually make lots of inference about what other people are trying to do. And so that's a very general mechanism that they use. And so that's why we try to transpose it in this artificial agent setup, is to have a goal prediction as a means of communication, basically.
Yeah, because I was thinking about learning, and usually what is done is like you have the basis and you train people on the basis, and then you go to more complex stuff.
Yeah, and so that's a very important complex concept in this type of research. Also, is the zone of proximal development, ZPD, ZDP, and something that's a lot that's implemented a lot is always trying for the teacher to give teaching signal that is not too hard for the learner or not too easy as well, and trying to find this soft spot where if you give this information, then it will maximally help the learner. And that's basically what real teachers are trying to do with students as well. You know, like if you're giving a test that is too easy or too hard, you're not helping the person really learn. And so you have to be in this soft spot. And then we come back to this as well. You have to understand what is the level of the learner, and so you have to have a general model of how the other agents think. And so that's completely related. And in this approach, in the approach of my friend here. In the reinforcement learning approach, he actually uses some of this insight with zone of proximal development here. Okay, thanks.
Maybe one last question.
Yeah.
Thank you for the talk.
Thanks.
Can you go back to the slides where you compare the two policies of the two teachers? Yeah. So just it went a bit fast for me, but so your interpretation is
So you
okay. Goal one is this, and like the goal is to have the best examples, like the less ambiguous examples for goal one for a potential learner. What you said is that if you start with
orange,
yeah.
then the possibilities are either
goal one or goal 1 and 2.
Yeah, right. Either this, or this. So if you if you start with orange, it's either this or this. Okay. So basically, when you start with orange, it might be goal 1 or goal 2 or goal 1. So it might be goal 1 or goal 2. Otherwise, if you start with pink, the only possible goal, if you're trying to communicate, is goal 1.
You said that there was a goal 0. Which
Yeah. So yeah, I see what you mean. But okay, so what you have to see here is that the policy for the pedagogical teacher for the goal 0 always starts with the third color, which is purple. Because I guess here we didn't see, or I didn't make it really clear.
Okay,
but here, so it's not really clear. This is orange, pink, and purple.
Okay.
Sorry about this. And so basically, the purple one.
Okay.
When you do the purple one, it's
sure that it's going to be equal to
yeah. And that's why here, considering the whole policy, it's always starts with purple for goal 0, pink with goal 1, and orange with goal 2. And that's how it disambiguates itself.
Perfect. That's ambiguous for me.
But that's a good catch.
All right. Do you have any other question? I have one. Do you also have a real arm with 7 degrees of?
Yes. So that's something I didn't mention. I should have mentioned is that the fetch robot actually exists in real life. Okay. So it's a manufactured robot by a company that we already use, and we have also like another type of robot, so the Dexter, I think, or something like this, and that's
scary.
Yeah. And it's a really weird one, like really huge one that really doesn't work pretty well. It's really clunky, but the pet robot is it's cool. I've worked with actual robots in the past. It's a pain. It's a real pain, and I'm not interested in this anymore.
That's very clear.
For me, it's a waste of my time because I'm not good enough at programming in ROS and things like this. It's for me. I will stick with Python.
All right. If there are no more questions, I think we can thank you again.
Thank you very much.
Thanks everyone online, and see you soon.
Yes.
I guess.
Thanks, bye.
Bye, Elena.
Bye.